Okay, we will record. So we've got a hydrogen atom. We're going to look at the magnitude of the electrical and gravitational force between the two particles. And if you remember back to chemistry talking about the development of atomic models, one of the big issues with the planetary model was why it doesn't, why it is able to sort of be stable like this. And when we get numbers, we'll take a look at that. Okay, so Coulomb's law says that the electrical force between any two charged objects, and here we're talking about point charges so we can kind of disregard mass, equals our fudge factor, Coulomb's constant, times the charge on object 1 times the charge on object 1 times the charge on object 2 divided by the square of the distance between them. And we're given all these numbers. I'm going to set that inside my atom. Coulomb's constant is 8.99 times 10 to the 9th Newton meters squared over coulombs squared. Charge is given in coulombs, and distance between them is given in meters. Now, the thing to remember, we're inside an atom, so we're dealing with really tiny little numbers. And I'm going to tell you right off that I love the TI multi-views. I don't love the way they handle scientific notation, though I just figured out one trick today that it's apparently taken me 10 years to get to. So we'll look at two ways to use your calculator to solve this. Okay, so F electric is going to equal, well, Coulomb's constant is 8.99 times 10 to the 9th Newton meters squared over coulombs squared. That is times. Now the charge on a proton and electron, they're equal but opposite. So one is negative 1.6 times 10 to the 19th coulombs. One is positive 1.6 times 10 to the negative 19th coulombs. It's a tiny little bit of charge. It's not a whole lot of charge. Because we're just looking at the magnitude of the electrical force, we're going to ignore the charge. Now we know, because those are opposite charges, this is going to be an attractive force. And that's just the question we would ask ourselves every time. So I'm going to plug in those numbers, and those are coming straight from here. And the distance between them, you want to talk about tiny, 5.3 times 10 to the negative 11th meters. And we're going to square that. Now, the issue that I take with the way your calculator handles scientific notation, I did solve, but I'm going to go ahead and do it sort of the way that I'm accustomed to doing it, which is the workaround that I figured out first. So I'm going to take 1.6 times 1.6 divided by 5.3 squared, the whole lot times 8.99. So this is just using the scientific notation sort of the old-fashioned way, times 10 to the, we're going to have a nested thing here, 9 plus quantity, negative 19 plus negative 19 minus, oh, this is going to be terrible, isn't it? Absolutely, utterly awful. I got the right answer both ways. I was really happy about that. Minus negative 11 minus negative 11. Yikes. Shall we get a number? Okay, so far I've got 0.8193, blah, blah, blah. Now, what does my power of 10 work out to? It's not that bad. It's just ugly. Let's do everything in the parentheses. You have your power of 10 yet? It's a little ugly. Everything in the parentheses I got down to negative 16. How is that? Did you get that? Okay. And so we come up with a final of negative 7. Somebody had asked, I had paused the video for a second, why are both the 19s negative? You have to be really careful here. The charges, one of the charges is negative, but the powers of 10, or I'm sorry, one of the charges is negative, one is positive. The powers of 10 are both negative. And that is a really common point of confusion. When we get to math, same thing, same mistake can be made. These are teeny, teeny, teeny charges we're dealing with. Okay, so this means we have to move a decimal. Those of you who've been with me through a few adventures know I hate this part. So let's see, negative, we're going this way. So to go back one more, it would be 8.2 times 10 to the negative 8th. And what are our units here? It's force. Newtons, yeah. So that's the magnitude of the force that is attracting those two things to one another. Okay, so that's an attractive force. Let's do the gravitational force, because that's what they're asking us to do, is to compare the electrical attractive force and the gravitational attractive force. All right, so with gravity, which we haven't talked about, force of gravity here, and this is more than your simple old mass gravity, because we're talking about the gravitational attractive force between the two objects. So force of gravity is equal to the gravitational constant, which is 6.77 times 10 to the negative 11th Newton meter squared kilogram squared, times mass of object 1 times mass of object 2 divided by the distance between them cubed. So the gravitational attractive force between these two things, well, 6.77 times 10 to the negative 11th Newton meters squared kilograms squared. Let me move that over a little bit. Here's where we talk about the convenient fiction that we've all been laboring under in chemistry. Well, no, we haven't been laboring under that one exactly. So, okay. We know that electrons are really, 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 really tiny. I mean, protons aren't, big hulking monsters themselves, but electrons are, they make protons look like, heavyweight wrestlers. So the mass of the electron, well, we'll do the mass of the proton first. Mass of the proton is 1.675, nope, that's a neutron, sorry, 3 times 10 to the negative 27th kilograms. It's pretty little. And mass of the electron, 9.109 times 10 to the negative 31st kilograms. I always think of Halloween when I see the mass of an electron because of that 10 to the negative 31st. 1031 Halloween. You're welcome. It'll help you somewhere down the road, I hope. Now the distance between them, we already have that. We used that in the first problem, 5.3 times 10 to the negative 11th meters, and that's going to be squared. So I'm going to use the same methodology. Yeah. Oh, 667. Thank you. Yep, there it is. 667 times 10 to the negative 11th. Okay, so 6.67 times 1.673 times 9.109 divided by 5.3 squared. The whole bloody mess times 10 to the negative 11th times, well, let's see, no, don't come back to that. That's sloppy work, Moser. Okay. Negative 27 plus negative 31 minus, whoops, see, I almost did that there, minus negative 11 minus negative 11. Hoy, that's ugly. Okay, let's get some numbers. Okay, so the force of gravitational attraction between those two particles is really little. Yes?
Is that 3.36?
Did I miscopy? Oh, 3.61. What am I doing? Good Lord. I clearly am not fit to do any calculations today. There, is that better? Oh, that's a nice try too. Oh no. See, even when conditions are against us, we will attempt and we will eventually prevail if we all work together to find our mistakes. See, there's the life lesson. Okay, so magnitude of gravitational force, magnitude of electrical force. Electrical force is winning out big time here. It's very clear. So the assigned problems for this, yes, I'm really going to do that. Number, I'll give you a little bit of time to work now. Okay, so the only one that's assigned, just one problem, just so you can say you've done a Coulomb's law problem. So if you go on and you do, physics 3 at college, that just sounds really stupid. But if you go on to a physics course on electricity and magnetism, you'll have had at least you'll done one of these by yourself. Good Lord. Okay. Is it posted? No, there's no PDF for this chapter that I found yet. So you have to use an actual paper book. I know, it's dreadful. You're welcome to take a picture of the problems in my book. And that'll also have, I don't think I can. Can I?
Yeah. Take a picture of the airplane.
Oh, well, here, why not? You can just airdrop it. Just number 1. We'll figure, I'll put it on Classroom. Yeah, you're right.